Swayam Prabha. Digital India. Educated India.
Start. Okay. Good morning everybody and welcome again to our course on Introduction to Mechanical Micromachining. In the last class we have seen some of the aspect of diamond turning machining, and we have seen that there are different ways we can do machining of different type of components like a concave type, convex type, and some free form surfaces also by utilizing XZ and C or B axis machining. And we have seen two classification, one is the hard loop machining and another thing is the hard loop soft loop polishing or hard loop polishing. And it was found that diamond turning is considered as a hard loop finishing process because we have to maintain the tool path with respect to the workpiece, or it is not like a multiple point contact machining, but it is a single point contact machining. So, let us continue further our discussion on diamond turn machining. So, this thing what we have seen in the last class is the hard loop finishing technique. So, here what we required, it is a single point contact. So, it is not self correcting similar compared to the soft loop polishing. So, let us see that how the material removal takes place in both the cases. So, first let us take about the hard loop finishing. So, here we are talking about diamond turning machining, and this is what we are doing in the diamond turning machining. An equation is similar to what we have used in the conventional machining process like a depth, feed and the speed, and where the D is the depth of cut, mostly it is in millimeter. When we talk about conventional processes, feed rate is also millimeter per revolution, and cutting velocity we consider as a millimeter per minute. And when we get all this value, you can find out material removal rate in terms of millimeter cube per minute. So, here what is important, that here we know that only single point is coming into contact. So, that is the reason that depth of cut you can actually predict very easily how much you are going in the Z direction. Feed rate you can set it, and velocity also you can set by that mean. But if you consider soft loop polishing, this equation cannot be used here. So, here what is happening, that there are multiple abrasive particles which comes into contact with the surface. So, depth will be different because some bigger size particle will indent more. So, depth of cut will be more for that cases, and some particles small particles which will penetrate less in the workpiece. So, that time depth of cut will be less. So, here depth of cut cannot be used as something like that. Feed rate, here what is important, that how you are moving. So, that is actually the cutting velocity, not the feed rate. So, feed rate is not coming into picture here. Velocity is playing important role. Other than velocity, what is important, how much you are pressurizing from the top. So, that is the right, cutting velocity and pressure play important role in the soft loop polishing or the loose abrasive machining. So, here for material removal rate, actually there is one classical equation available, that is called Piston equation. So, what this equation tells, so the average MRR is proportional to dt by d capital T by d small d equal to C, P and V. So, let us see what are these parameters. So, P is the pressure. So, this pressure is how much pressure you are putting from the top. That means, suppose you, this is the abrasive particle slurry at this line, and then you have to put some pressure from the top, then only this particle will indent into the surface. So, right. So, that is related to the pressure part, and then you have to give a relative motion between the workpiece and the lap part. So, that is called the velocity. Now, what is this thickness? Now, initially what we are looking here, right. So, suppose what is happening, that suppose this is your initial surface on the workpiece, and this is the tool or lap which you are moving in this direction. These are the small abrasive particles. So, when it is moving, at that time what is happening, that it is removing some of the material from the workpiece surface. So, that Z height is that how much amount of material is removed in 1 minute or 1 hour, or that is called the Z height. So, this is the T. So, that is the dt by capital B by small d is equal to the rate of reduction in thickness of the workpiece, right. So, by that way you can actually find out the how much is the reduction in the thickness with respect to time. So, pressure is more important because when if you do not press the water, it will not indent inside, and velocity is required because after indentation of this particle. So, this is the particle, it is indented into the surface. So, this is the surface, and once it is indented by normal force, then it should translate in this direction. So, this much amount of material it can remove. So, that is why velocity is also important. Now, there is one thing that is called Piston coefficient. Now, we know that many things are playing important role other than pressure and velocity. If you change the particle size, then things will behave differently. If you change the particle type also, because suppose you are using a silicon carbide and then you use diamond particles, then things will change. At that time, all these parameters other than pressure and velocity, you can actually fit into the piston coefficient. So, now you can see here. So, this is actually not more predictable. So, this is more we are talking about the average MRR, and here what is it is predictable because we are actually fixing these all three parameters, and which is not possible here. So, in our hand, what is our hand, that is the pressure, how much load we can put from there, and then the velocity. Rest of the things are random because some particles will indent, some particles will not at all indented, and these are the things which makes this particular soft loop finishing process more unpredictable. This graph we have seen in the micro cutting operation also, but still it is relevant to this particular process, because here what we are doing, we are actually doing machining at this particular level. So, this is the normal thing where what is happening, that here you have to find out the grain boundaries through which the material removal takes place. So, wherever your tool is coming into contact or it is passing through the grain boundary, then there is a removal of that material in form of chip. But if you reduce this particular uncut chip thickness, then what is happening, then it will around the 10 micron or something, then it is looking at the defects within the grain. So, now you have to look around the dislocation or some other things which will create a or which will allow this tool to pass through the cutting edge. So, this is the second thing, and if you go further inside it, when your uncut chip thickness is less than 1 micron, then this is what is happening. So, then you are actually looking at the atomic scale, where you have to find out the what are the vacancy and the dislocation, something within the dislocation part, atoms and everything. So, here this what we can say defects at the within the dislocation, you have to find out in such a way that particular location will become the origin of the breakage, because our objective is to get a uniform chip thickness, so that you can get a material removal very efficiently without any problem. So, here the material removal takes place at that level. So, this graph is also relevant to the diamond turning. Now, let us talk about the ductile regime machining of the brittle material. Now, we can see here that brittle material mostly actually we can get the discontinuous chip in the brittle material, but you can actually cut this brittle material in the ductile regime. Now, take this example. Now, here what is happening, that indenter is gradually indenting the workpiece surface. So, this is the initial contact between the indenter and the surface, and you can find out a small amount of dimple will be created. And if you continue further indentation, then what happens, then lateral crack and the this crack particularly will start forming, and then it will remove the material in terms of some of the craters. So, indenter with a minimum tip radius is gradually forced into the brittle material surface. A minute area on the workpiece exhibit the elastic deformation first. So, this is that area what we are talking right now, and then plastic deformation, finally the micro cracking. So, this micro cracking will take place if you further continue your loading. So, plastic behavior in ductile mode occurs in the limited area over a small cutting depth. So, now our objective that if we cut any brittle material within this depth of cut, so let us consider this, we consider as a depth of cut, correct. So, if we work within the depth of cut, then what we can do, to actually cut a brittle material in the form of a ductile machining. So, that is why it is called the ductile regime machining of a brittle material. We are not actually going into the brittle mode, we are more restricting ourselves within the ductile regime only. So, let us see how this can be done in the diamond turning. So, our objective or our more focused is on the depth of cut now, because now we know that if you maintain your depth of cut less than or equal to this particular phenomena, that also depends on the material and the type of indenter, but if you maintain that thing, then you can actually do cutting of a brittle material in a ductile mode. Right. So, when actual depth of cut becomes considerable means when it is higher, then material gets removed in the brittle mode accompanied by the some cracking. So, we have to work within that area. So, now this is the very classical figure, and mostly it is used for explaining this ductile regime machining of a brittle material. What it tells us? So, here this is the diamond cutting tool, and then this is the feed rate. So, when you give a feed rate in this direction, this is the chip thickness, whatever it is a variable, 0 at this particular location and maximum at the top surface of the workpiece. Now, when you cut a brittle material, at that time what happens, there are lot of cracks generated just before the deformation or the before this uncut chip thickness. So, what is our objective? That we know that our surface is this one, this is the surface which we require. So, this is our required surface. So, if you do not allow this particular indentation or the damage to cross this particular line, then we can sure that there is no defect or something generated because of the machining. So, now this YC, what is this YC? YC is the surface damage depth. Now, right now it is entered in this, so this is the cut surface plan. So, this is the surface what we required, and now this is the things which we do not require, correct. So, now this is called the critical chip thickness. Now, you can see the chip thickness is variable, 0 at this location, maximum at this location, right. But this is the one location which is very critical, that is why that if you do machining below this level, that means anywhere here at that location, at that time this YC will be within this particular zone, that is it is on the surface, it will not cross this cut surface plan. Then you continue this machine, because whatever these things are generated here, this will be actually removed in a subsequent feed, because feed we are giving in this direction, anything generated ahead of this tool, that will be removed in the machining. But if anything is penetrated this cut surface plan, then this cannot be removed. So, this will be a permanent damage to the or permanent defect to the workpiece surface. So, our objective is that this YC should not cross this particular surface, this line. So, that is our objective, and this particular DC will make sure that if you operate your machine, or if you operate your, or if you set your DC, that is chip thickness, uncut chip thickness below this level, you are making sure that this YC will not cross the plane surface, right. So, ductile response is obtained when the depth of damage YC initiated at the cutting depth DC. So, this is YC, that is initiated DC, does not extend below the plane of the cut surface. So, that is our objective. So, if you cut a ductile within the ductile regime, then there is a high chance that this YC will not cross the surface. And now, this is the 3D view of this image. Now, it is also showing the same thing. Now, these are the cracks generated at this location, and now you can see that this is the machine surface which is generated after machining of by diamond cutting tool. And you can see this YC, if you maintain this, and here you can see this is the maximum uncut chip thickness, that is exactly at the top surface of the machine's component, and this is somewhere here it is showing the critical chip thickness, and that is showing at this particular YC. So, anything generated here, you can see that there are some more cracks are here, but we know that our surface is here at this location. So, anything which comes at this location, that will be removed by the diamond cutting tool at the later stage. So, our objective is to do cutting at this particular DC or lower than DC, and we know that this DC will change depending on which type of material you cut. So, let us see that how this DC will be calculated for different regions. Right. So, this is the threshold chip thickness, that is what we are talking HC right now, because we earlier in that micro machining of mechanical methods, we use HC as a term, but that is why we let us continue HC. In earlier case what was DC, that is the same as HC. So, that threshold chip thickness is given expressed by this particular formula. So, here A is the constant of the material, because we know that this particular threshold chip thickness is variable depending on the material which we are using. Then elastic modulus is the E, H is the hardness of the material, Kc is the fracture toughness of the material, and by that way actually you can find out Hc of a different materials. And these are the Hc value in terms of nanometer. Now, you can see that if you want to cut silicon in a ductile mode, then you have to select a Hc value lower than 200 nanometer. And similarly that there are 2 or 3, because earlier some other researchers also suggested 236 Hc value for silicon. Then then there are some of different type of ceramics material available, then nanocrystalline. You can see that how much depth of cut you have to maintain. Now, if you want to maintain this depth of cut, and if your machine is not capable to give this much amount of depth of cut, that means by means of penetration of the tool into the workpiece. So, your penetration should not cross the 200 nanometer. Now, which particular system will give you this type of resolution, that is you have to use the linear motors and some type of aerostatic bearings, then only it is possible to work within the nanometer region. Otherwise, whatever ball screw type of things and some other type of where mechanical contacts are more and friction and wear is more, at that time you cannot get this type of resolution at the nanometer scale. So, that is the why diamond turning machines are very costly, and similar the case for the micro machining center, because the technology which is being used for making this machine more and more robust and more accurate, that is the reason that you can get the accuracy at the nanometer level. Now, coming to the tool measurement system, because everything is depend on how accurate is your tool. Once you get the required tool accurate, then what is the second thing is the how you are fixing the tool on the tool post. So, that is the thing. So, one of the major source of errors in the DTM is the tool setting. So, what we are looking here, we are looking at the nanometer scale depth of cut, and if nanometer scale is the depth of cut, then your requirement of the rigidity of the tool setting also very important. So, if you do not set your tool perfectly at the x0 and z0, then there are lot of problems related to the machine surface. So, function of the system is to set up the tool with respect to the machine coordinates, because we have machine coordinate, our workpiece is located in the headstock, and then what you have to do, that you have to find out that at which location you are starting the machining. So, because in normal turning operation, what we do, that we try to align our what we say the nose radius with respect to the center of the workpiece, but that is not the case always in the DTM, because we know that we want to create some free form surfaces or concave and convex surfaces by different type of setups we have seen. So, at sometimes what happens, we do not require to go to the center, but we have to find some location onto the facing surface where we can start the machining for the different operations. So, position of the cutting edge is computed by knowing the following parameters. So, what we have to find out, first we have to find out x and z offset of the cutting tool, right. So, because mostly our machine is related to x and z only. So, this is our workpiece, right, and this is our cutting tool which is located at this part location, and this is the center. Now, when you are moving in this direction, this is the z direction, and when you are moving in this direction, this is the x direction, right. So, mostly in the x and z configuration, mostly this is normal, similar to our normal turning operation or facing operation. So, at that time we have to make sure that these things are actually aligning, that means this is coinciding with the center of the tool workpiece is coinciding with the edge of the cutting tool. Then you can do actually facing operation conveniently, there will not be any type of unremoved material, whether it is on the top surface or this surface. So, that is the one of the ways of setting this part. Second one is the tool nose radius, because tool nose radius is playing important, because now right now whatever you are setting from this particular plane, but if you see from the top surface, now when you see from the top surface, then your tool has a nose radius, right. So, we have to make sure that it is touching at this location, not at this location or this location, otherwise your program control will be different than the what you want to achieve. So, nose radius you have to maintain, right. Position of the center of the nose radius, that is what we have discussed just now, right. So, all these 3 parameters this measured by the tool setting device. So, there are tool setting device available, some of them are optical microscope which are attached over the cutting tool, and by some of the things which you can get this thing done by the some type of manual or some type of sensory elements. Then the tool center height adjustment, because we want to make sure that our tool is exactly lying at the center of the workpiece. At that time a minor change in that, suppose it is a few micron here and there up and down, then it is very difficult to get the center done, because when we are talking about the optical quality of surface finish, then even a 1 micron or 2 micron of adjustment is also very, very important. Even we are looking at the sub nanometer level of adjustment. So, this tool height adjustment is performed by the one of the things which is attached with the cutting tool, that we will see that there is one slide available for discussion of this part. And another thing is the waviness of the cutting edge, right. So, whatever we are cutting edge is whatever you are getting, mostly we will see something like this. This is, you consider this is the nose radius of the cutting tool, correct. So, now what I meant by look wise, it looks very sharp, but if you magnify it, then what you can see here, that you will find lot of irregularities on the top surface. So, here you will get some of the irregularities. So, these irregularities also play important role, because if at this particular location, if some of the peaks are very, very large, then the contact point will actually happen at that localized point only, not to the whole nose radius. So, that plays very important role. But this is the tool error, this cannot be controlled by the machine controller, because for making the or correcting the waviness, you have to fabricate your cutting tool in such a way that there is a less variation on the waviness of the cutting tool. So, this is not controllable parameter, but it is a tool parameter, but not related to the machine. So, now cutting tool, mostly our name is the diamond turn machining. So, mostly we use the diamond only, because diamond is very, very hard material, and it will not actually create any problem when you do machining on ferrous non-ferrous materials. So, that is the advantage. So, we use diamond, it is hard, but it is also brittle material. So, that is the big problem. So, hence the tensile stresses on the cutting tool edge are kept to a minimum, because we do not want to actually stretch the diamond, but if you put a compressive loading, we will not create, it will not create any problem. So, small to nose radius makes the lesser contact length on the workpiece surface. Now, if you see, this is the rake surface and this is the clearance surface, clearance angle, this is the rake angle, and this is the diamond cutting tool, and this is from looking from the top surface. So, this is the nose radius. Right. So, this is the nose radius what we are talking here. So, small nose radius makes the lesser contact onto the surface. So, now what we can see here, that suppose our workpiece is something like this is our workpiece, right, and we have a two tool with a, one is the nose radius is something like this, and second is the nose radius something like this much. Now, you penetrate this particular workpiece tool into the workpiece. So, now let us see that we are putting this thing, we are drawing one line here. Now, this is the line, now our workpiece located at this location, right. So, now smaller tool makes the lesser contact. So, now see our contact area is this much only for small tool, small nose radius, but for large nose radius our contact area is more. Why this is important? Because we know that we have to work within a very, very small amount of depth of cut. That is not only thing, but we have to maintain the forces acting onto the surface. So, force playing will be very, very high here, because area is more, so force is more. So, similarly here area is small and your force is small. So, you can retain this particular geometry of the cutting edge for a longer time if you want to go with a smaller nose radius. But smaller nose radius also play important, because you have to make it more and more sharp, but your life will be degraded. So, you have to actually do a compromise between the bigger, whether you want to go with a smaller nose radius or the larger nose radius, right. So, concave surface and the small nose, if you have machining with a concave surface, now suppose let us take that example. So, this is your concave surface, right, and you are using a small nose radius. So, let us consider this is the small nose radius, right, and what happens because of that, because of it is a concave surface. So, its contact will be very, very small at this location. But now if you see that if you want to use the same thing, but if you have a larger nose radius. So, now there is a under nose radius, let us see that. So, this is the under nose radius. This is larger than this one. So, at that time cutting length will be very large. So, wherever it is going to touch the surface, at that time we know that this is the cutting length. So, this cutting length will be very large at this location. So, sometimes what happens, when your curvature is very large, at that time you can actually go with a large nose radius, because if you are if you want to do machining very quickly, then you have to go with this one, because this way you can actually increase the cutting area here, and within a shorter time you can complete the complete this particular path. But if you go with this thing, it will take more time. But there is another disadvantage here, because we have seen here that if your contact is more, your forces will be more, and the life of the particular or the sharpness of this particular nose radius will be, or the cutting edge radius will be very less here. So, that is the reason that you have to see that which material you are machining, and then you have to set a parameter in such a way that you actually play around the cutting edge length, that which particular cutting edge length is enough to increase the production rate also, and that is enough to reduce the wear of the cutting edge radius. So, that is where you can actually play around the parameters. And these are the different photographs of the actual cutting tool. Now, you can see that most of these diamond cutting tools are the brazed one here. So, you have to braze it with the standard cutting tool or the standard shape, and then you can actually use this particular cutting tool for a micro machining operation, or the machining of a ferrous materials. So, what are the key features of this particular process? So, it is that nose radius is around 0.2 to 3 millimeter, even larger is also available for machining of a very large amount of surfaces. Sharpness of the cutting edge is tens of nanometer, because sharpness is very important, because we know that we have to give a depth of cut of a less than 1 micron, and we have seen some of the material where we have to maintain that uncut chip thickness or less than 100 nanometer or something, so to make sure that we can cut those brittle material into a ductile mode. So, that is why the sharpness of the edge is tens of nanometer. Accuracy or waviness of the cutting edge, that will play important role here, because now see in actual case what we are looking at. So, in normally what we see is this one, but if you magnify your cutting edge at a 40,000, then you will see this type of irregularity. So, this may be considered as a acceptable, because you cannot make something like this thing, that is impossible, but you have to maintain this unevenness or the roughness in such a way that it will not create any problem. But if you see at 40,000 and if you find out this particular thing, then it is a problematic. Now, what is happening? Now, see, this is the center of your cutting edge radius, that is nose radius. Now, what is happening, that this particular point actually it is inside, but this particular two cutting points which are actually projected away from this center point. So, now what is happening, that your whole program or whatever path you are giving to the cutting tool or the workpiece, then actually it is reference with respect to this point, not to this point. And when your workpiece comes to this location, actually it will come in contact with this particular location, not to this location, because this is more projected. So, this is the material removal takes place here, not at this location, this will take place here. So, your intended location is actually shifted to the different other location, and you are actually not able to control that particular location, and that will create a problem on the surface geometry or whatever features you want to create. So, you have to also find out what is the accuracy or the waviness of the cutting edge radius. That is the right now what we are talking about the nose radius, but if you see on this particular cross section. So, if you see this is the nose radius, and if you cut down this thing, then you will find this is the surface. So, this is the cutting edge radius, this is the cutting edge radius, and this nose radius is, this one is the nose radius. So, both things are important. So, we have to maintain the waviness and accuracy of the cutting edge radius also, as well as the nose radius. Okay. Now, how do you select the nose radius here? So, now let us see that this is the nose radius. If you are machining a smaller feature size, it is better to go with a nose radius, small nose radius, because we know that smaller the nose radius actually you can reduce or you can actually control the contact point very easily. So, smaller feature you do not want to come across this type of problem, because now you know that there are a lot of problem if the contact point is different than the reference point. So, it is better to go with a smaller nose radius. Fragile job, better to go with the smaller nose radius, because we know that if your nose radius increases, your contact point or the contact area increases, and we know that for fragile job even a small amount of additional load is enough to break those components. So, better to go with a small amount of loading, and to make sure that loading is small, then your tool nose radius will be small. External feature, better to go with the large nose radius, because now what is happening in external features, now we know that this is a convex surface, right. You want to do machining at this location. Now, with going with a smaller nose radius, what is happening that you have to spend lot of time here, and since it is external surface, so your nose radius has no connection with the what are the features available on the surface. Now, you can see that this is the features available and your nose radius is this much, then what is happening that you will actually not able to penetrate to the extreme position. That is going to happen if the features are the internal features, but these are the external features. So, it will not make much difference in this case. So, larger or external features, but again it depends on which type of workpiece you are cutting, but mostly if in general statement the larger the or external the feature, it is better to go with the larger nose radius, so that you can actually do more amount of cutting operation and you can finish your tool path very quickly. So, these are the different ways you have to select the cutting tool, and these are the parameters, because our cutting tool material is fixed, but within the material we have to play with the different type of parameters. One is, these two are the very important, one is the cutting edge radius and another is the nose radius. Then we have to find out, because diamond you can actually do machining with a different because there are different type of planes available, 100 plane, 100, 110 and 111 plane we have seen in terms of silicon, right, in the some lectures long time before, and we have seen that this is very difficult to cut and this is very easy to cut. If you cutting is easy, that means its wear is also very high. So, we have to also see that which particular plane is coming into contact with the workpiece, that means what is this particular plane and which plane you are making the cutting edge radius and the nose radius. So, depending on, there are lot of processes available by which you can actually manipulate this particular plane, and you make sure that the hardest plane is coming onto the surface and you can do machining for a longer period of time. So, let me finish this lecture here. We will continue this topic in the next class. Thank you very much.